Welcome everybody to MEERTALK. My name is Kaeza Fern, and I'm the Director of Communications at MEER. We are really glad to be getting together for another MEERTALK today. And before beginning, I just thought, because of our topic, that we could, for a moment, we're going to be talking about resources on Earth, and for a moment we could just pause and consider all of the resources that are part of our own lives, our daily lives, our lives here on the planet. Today, we are going to be hearing from our guest speaker, Professor Simon Michaux, Professor of Geometallurgy at the Geological Survey of Finland. Then we are going to have a question and discussion period with a couple of people from various sectors. And after that, we will open it up to audience questions. So you will be able to put those questions into the chat. Before we begin, I'd like to give you some updates about MEER. We are working to set up a mirror and cryosphere experiment, and we would be very grateful for any donations that you can make to support the shipping of the experimental materials, which include mirrors and other devices. So to donate, you can go to meer.org/donate, and we are very grateful. If you have any questions or want to be in touch, you can always email community@meer.org. Here at MEER, we're very cognizant about the issue of feasibility, energy, and material requirements. So in that spirit, today, Professor Simon Michaux will be talking about the feasibility of going off fossil fuels. And I'm going to first talk to you a little bit, tell you a little bit about Simon. Simon Michaux is Associate Professor of Geometallurgy at the Geological Survey of Finland in the Circular Economy Solutions Unit. He has a Bachelor of Science in Physics and Geology and has a PhD in Mining Engineering from Julius Kruchnet Mineral Research Center at the University of Queensland. His long-term objectives include the development and transformation of the circular economy into a more practical system for the industrial ecosystem to navigate the twin challenges of the scarcity of technology minerals and the transitioning away from fossil fuels. If anybody has any questions while Simon is presenting, then you could send them along to Bud in the chat, and Bud will be showing up as the co-host. So Simon, we're so grateful to have you, and thank you
Hello.
for coming.
You're welcome. You're welcome. Hello. So it's very nice to meet you all. The MEER platform sounds amazing. Some very interesting ideas you're working with. So I'm going to show you today a summary of two pieces of work, which are like bookends. The mineral supply challenge to phase out fossil fuels. The origin of this work was a simple question my manager posed to me over a cup of coffee of how does the European Union source minerals to source the mineral supply for the gigafactories that Europe's going to build. How much minerals and what kind and where. And when I started doing this work, it became apparent that the basics hadn't been done. So I went and did them myself. But before we get to the work, I'm going to show something that I've been developing for some time to show that the change is in fact happening now, that this is not a theoretical thing that might happen in our future. All right, so what you're looking at here is all the metals that the World Bank uses to track the health of the industrial system, the base metals, the precious metals, and oil, gas, and coal. And so what I've done here is taken the data as far back as I can get, which was 1960 in a month-by-month basis. And I've overlaid them by indexing each curve to the number 100 and December 2001. And so everything was a reference point to that. And so the idea of doing that is to show periods of relative stability. And so prior to 2005, things are relatively stable. with the exception of the 1979 Iran oil embargo. But after 2005, that happened. Something blew out. Now, I make the case that this blowout started in a chain reaction that started in the oil industry. Now, that put a strain on the rest of the system, and that later created the global financial crisis, what we call the GFC. Now, the largest economic correction since 1929 was not enough to address whatever the problem was, and so that volatility is still there. So whatever that was, it is still there. The purpose of this chart is to show that this is not an abstract thing that might happen 50 years from now, or we're discussing something in theory. This is an observation that the change started 17 years ago. We're in the change now. Right, so here's the first piece of work that was put together. This was the assessment of the extra capacity required alternative energy electrical power systems to completely replace fossil fuels. That is, how do we replace the existing system that we've got around it? No more chit chat, no more discussion. We will now do it. So what I first did is, well, what was the physical task done industrially by fossil fuels, and determine the useful work done, so the true scope, with the understanding that every energy system has an energy efficiency. So once we had that, assembled the non-fossil fuel technology that we could get at the time. What's coming off the market? We have to do this now, so it's commercially available now. Summed it all together and calculated the extra quantity of electrical power we will need. Now, the first generation of work was if we were to expand the existing non-fossil fuel mix in 2018 up to the need amount, how many fossil fuel power stations could be needed. The second generation of work was to use an energy split that the IEA has recommended in 2022. So in this report, we have the number of vehicles by class, number and size of batteries, an understanding of when you'd use an electric vehicle and when you'd use a hydrogen fuel cell. Estimates of the maritime shipping and the rail systems in both electric battery systems and in hydrogen fuel cells, and estimates of what we would need to do to phase out fossil fuels for things like gas and coal power generation. I examined the concept of expanding the nuclear power plant fleet and the possibility of using biofuels, if so, where, and plastics and fertilizers. So what this report does, it was tried to catch everything in, but it did not catch the fossil fuels consumed by industry directly to generate heat for manufacture. And that accounts for about half to 60% of coal and about 40% of gas. So what we have here, the numbers I'm about to show you are not only conservative, but they're just simply too small. So what would it take to replace the system? Now, assuming we're going to move as fast as we possibly can to phase out fossil fuels and implement new technology like solar panels and wind turbines. The faster we do it, and it's going to be so difficult to actually predict what that will be 5 years from now, for example, but there comes a point when the existing system is fully replaced. When you walk down the street, all the cars and trucks you see will not be powered by fossil fuels anymore. All the power that is generated, that comes on the lights in your computers, is no longer fossil fuel generated. So what is that system? And then once we reach that point, well, okay, we'll settle into a more stable growth, or so we would like to think. So my report was to model that system. Presumably, it's in our future. Now, the European Union in 2017 committed to 100% done by 2030. Well, that's what they would say in meetings. They formally committed in Parliament recently, a year or two ago, I suppose it was, with 30% will be done by 2030. Well, 30% of what? And it turns out not really many people have actually thought in these terms. So what's the true scope to phase out fossil fuels? So I looked at the existing transport fleet in 2018. Cars, trucks, trains, planes, automobiles, aircraft. I did this for the United States, Europe, the European Union as in the EU28, China. I mapped the Chinese government. That was an experience. And the fourth calculation was the globe at large. So there are 4 calculations running in parallel. What I'm showing you today is the global calculation. And that gave us the number of units, required batteries, and what have you. Now, in 2018, 84.5% of global primary energy was still fossil fuel based. Less than 1% of electric vehicles, of passenger vehicles, sorry, are non-fossil fuel. The majority of the system has still yet to be manufactured. And as that is the case, it cannot be recycled. You cannot recycle what something hasn't been built yet. So this is a mining problem. For the first generation, it must come from mining. And there was the required power grid expansion, and that led to the required power storage to manage intermittent supply. And that has proven to be a sore point on Twitter in particular. How big must that power storage be? And my numbers are much larger than anyone else's, and that is having implications. If you couldn't be bothered reading the report, fair enough, just read this little black box. Current plans are not large enough in scope for the task before us is much larger than the current paradigm allows for. Baseline calculation went like this. When I first started this, I asked the basic question, how many vehicles were there in the world? And I couldn't find a single report that actually had a defendable answer to that. So I actually did the work myself. And this is a very crude estimate. It's out of date. 1.4 billion vehicles travel a little under 16 trillion kilometers. The real number is probably close to 1.5. It's a crude estimation, but it was the best I could do. Now, because everything was electric and everything was calculated as hydrogen as well, I was able to do some interesting comparisons. So let's compare electric vehicle systems against hydrogen fuel cells. And what I found was the EV system had a battery mass 3.2 times the size of the hydrogen fuel cell tank. But so it could go 3.2 times further or last 3.2 times longer if you had a hydrogen fuel cell. Right, so, and that was just as it sort of came out. But if we're not going to use natural gas to make that hydrogen, hydrogen's an energy carrier, not an energy source. So we required 2.5 times the electricity to make that hydrogen compared to charging the equivalent electric vehicle battery. So you put those two together and we get this. All short-range transport should be electric vehicle systems. Anything that stays in a city or has a range of, say, 100 kilometers. I don't know what the real number is for that range. That's an engineering calculation to be done by others. But all passenger cars, commercial vans, delivery trucks, 1.39 billion vehicles, they'll do 14.25 trillion kilometers in a year. Now, here's the important part. To do that, we need 65.19 terawatt hours of batteries. Now, all other studies I've seen have that the number of batteries looked at is in gigawatt hours. I'm terawatt hours. I think what's happened here is other studies have misdiagnosed the size of the global fleet of vehicles. They're not including trucks, they're not including trains or maritime shipping at all. It's just not there. And all long-range transport should be hydrogen fuel cells. All the big semi-trailer, Class 8 HCV trucks, any rail transport that goes between cities that does freight, anything that's a diesel locomotive should now be hydrogen, and the entire maritime shipping fleet. Now, to be understood, all of these things can be electric vehicle. The engineering does exist. This is a straight logistics efficiency cut. It actually makes more sense efficiency-wise if everything long-range is hydrogen fuel cell and everything short-range is electric. It's not a question of engineering viability. We will need 200 million tons of hydrogen for that hydrogen economy. So this is the electric vehicle fleet, and that's the amount of power we will need to charge the batteries across 1 year. So to phase out other industrial applications like gas and coal power generation, heating of buildings, and the coal-fired steel manufacture into something else, we will need a little under 20,000 terawatt hours. The hydrogen economy, that number of vehicles travel that distance, and we'll need that amount of hydrogen, but we will produce it and we'll need that amount of power. So I looked at biofuels. Biofuels could be the most sensible way to keep the aviation industry going. It could be the only way to keep the plastics industry going with bioplastics. Also, our food and fertilizer will most certainly have to be sourced organically, which is all feedstock from the environment. But at the moment, we're actually over our skis already. So a sustainability audit that looks at these things directly with both economic sustainability and biodiversity sustainability, and a bridge between the two has to be embedded in that study. And right now that doesn't exist. And so there is a great big question mark over what can or should come from biofuels. So now I'm going to come to the energy split that in 2022, ARENA released this very nice report where they made a prediction in 2050 of what the energy split would be. Most of it's wind and solar. They have a little bit of gas there, so I took that out and I used some assumptions from my previous work. And so I had an energy split, which is on the slide after this. So given that energy split, let's put our energy systems together. We need 36,000 terawatt hours in a year. Now, according to that split, we need 586,000 new non-fossil fuel power stations of average size. Put this in context, in 2018, the fleet was 46,000 stations. That is the difference in energy return and energy invested. I collected some statistics of what each system actually did, and I could run some statistics on it. So what did the average system do? Not what they promised, what they actually did. And so you apply that split and you get this amount of stations of average size. Now, a lot of this is not practical, but if we're to hit that target according to those splits, that's what we need to do. The basic outcome of my work is the current plan is a crap plan and we need a better one. So don't for a moment think that I'm suggesting that this transition won't happen, because it not only must happen, but these are the only options we have for now. It just won't work the way we think it will. Now, what's the elephant in the room is power storage buffer. Wind and solar are highly intermittent, right? And so that power storage buffer at the moment is believed to be battery banks by our policymakers. There are other technologies, but it's the battery banks is what they've bet on. So let's look at that. So if we were to deliver 1,000 terawatts of power over a year, so these are all the systems that were in 2018, according to the Global Energy Observatory. And I had a couple of thousand power stations across the world in all the different groups. So I ran some stats. Nuclear is our clear best provider, but it's the end of a very complex and expensive and vulnerable value chain. I actually looked at expanding the nuclear power plant, but the answer is it cannot expand fast enough to be useful, and the large volumes of spent nuclear fuel at the end of it is going to become a serious problem if it does expand. So the IEA believes the future is wind and solar. Now, if we were to replace 142 coal-fired power stations, delivering 1,000 terawatts per year, 142 coal-fired power plants, or 30,000 solar PV stations, right? The sheer efficiency and power of fossil fuels is going to be tough to replace. We have to face the fact that renewables may have a much lower energy return and energy invested ratio than fossil fuels, and may not be strong enough to replace fossil fuels in the next industrial era. And that implies that the renewable energy systems are not the foundation for the next industrial era. They're a stepping stone to something else, and we don't know what that something else is yet. And if we don't get that alternative, then we are just going to step into a very low energy future. Right, so here are these numbers graphically. The column on the left is what the power was generated in 2018. So they're the non-fossil fuel systems we've got. That's the stuff that needs to be phased out, oil, gas, and coal. And the column on the right is the green one. This is what we need to construct to replace the existing system. Now, we are talking about building an electrical system substantially larger than the existing one, using very expensive and fragile energy. Context, total power in 2018 was 26,614 terawatt hours across the year for the globe. The jobs are charge the batteries, make the hydrogen, electrical power generation to phase out gas and coal, heat the buildings, and to phase out coal-fired steel manufacturers, the little sliver across the top. So this is our job. This is our target. So that energy split that I mentioned before from the IEA, combined with my work, as in we're phasing fossil fuels out completely, I came up with this split. And as you can sort of see, wind and solar take up the bulk of it. And this is where the 586,000 power stations come from. Now, let's talk about buffer. Supply and demand must balance. In fact, it must balance to a millionth of a second. If it doesn't do that, we get what's power blackouts and power spikes, and the grid tears itself apart. Here's a snapshot from Canada for a couple of weeks. No, a couple of days, sorry, 5 days, I think it is. Okay, nuclear is pretty stable. It can't move around. But you might notice supply and demand does go up and down with a day and night cycle. Hydro can vary a little, but only a little. It's gas. The gas can actually turn itself on or off at will and deliver power pretty quickly. Now, wind and solar were so variable that they're just not useful. But it's the gas industry as the buffer. And if we phase out gas, we have no buffer. And that's something that I have not seen anywhere in the literature. This is wind, solar radiation in Germany. I think it's in Berlin, across a year. There's simply less sun radiance in winter than there is in summer. Fact of life. So not only is it varying day and night, and it's subject to weather being overcast and what have you, but you've got a seasonal variation as well. Wind. In 2014, the UK Parliament did a study on wind, and they found that power production was so erratic it could not be predicted. And reliable capacity as a percentage of the maximum capacity of the grid was only about 7 to 25%, but they couldn't even pin it down to that with better resolution. So variations in power produced can last weeks, in some cases months. Now, looking at those stats that I showed before, across the calendar year of 2018, solar PV was producing power 11.4% of the year, and wind was producing power 24.9% of the calendar year. Both of those need a buffer, or we just completely re-engineer our grid to allow for variable power. So demand can function on a 48-hour buffer. We could probably do that. That'll outmaneuver all the weather issues. But supply is where you need the large buffer. Now, I've actually, in the literature, they recommended, there were several things. One was 1 month. I selected 4 weeks for just wind and solar only, not the whole system. So it's conservative. If you've got the time, look at this presentation by Jan Bloemgren. He talks about the practicalities associated with power sharing and balancing of renewable power. Right, so this is the second generation of work. We've got this energy split. We're going to look at a buffer for just 4 weeks of wind and solar. We're not even going to use solar thermal, just PV. In the literature, they had 48 hours, and that's obviously not going to be enough. But they also recommended 1 month. That was the best reference I could find. So that's for the whole system. I selected 4 weeks for just wind and solar. But if wind and solar are actually 72% of the grid, wind and solar may not be viable in a large grid because at the moment, all existing wind and solar is stabilized by something else. Like all the wind in Denmark stabilized by power from Germany or power from Sweden. If the grid is so large, what's going to stabilize it? Anyway, so these numbers are pretty conservative. We need 2,000 terawatt hours. That is actually 30 times the size of the electric vehicle fleet in this simulation. And that size number there is so large, and that's what a few people on Twitter have got their hair on fire over. But according to this very conservative estimate, that's what we need. So these are the number of systems that we need. We've got electric vehicles and their batteries, hydrogen fuel cells, wind turbines, solar panels, and power storage batteries down the bottom. This is our target. And remember, this is just one generation. All this stuff wears out after 10 to 20 years. And then we go again. Watch this. Oh, so in this report with the IEA, Role of Critical Raw Materials in Clean Energy, they started to quote what is the metal content of each of the different systems. And there was a whole lot of these things. There was, they also had market share. Like these are wind turbines. There's 4 there's 4 models of wind turbine that are going to dominate the market. And so in the year 2040, the future, what will dominate where, both onshore and offshore? So we've got estimates of what's in each one. And then we've got the metal content in each system. So you take these contents, project them onto the needed number of turbines and solar panels that we've already got based on the previous work. Sum it all up together. They also gave, thank you very much, all the battery chemistries. So now we're in a situation for light-duty vehicles and heavy-duty vehicles. We've got an understanding of what's going to be in the market in 2040 or the future. This is what they think. Never mind what we are now. In the future, what will we be? And so we're able to sort of develop things like, this is the split that was actually worked out, market share. And then that market share can then be projected into, well, the different chemistries. This is power storage. And then leads us to a situation for by chemistry, battery chemistry, we've now got a quantity of metals going into each one for the whole global system. Now, there's about 36 tables in this calculation, and all of this is going in a report. If there's a paper in that's in peer review at the moment, but I'm actually wanting a report as well, so I can actually put all tables in so it can be looked at. So now we get down to this situation here. For each task, for example, metal content in all electric vehicle batteries. According to metal, we've got their full tons. And then we got all the different tasks for the needed geothermal power construction, or the needed nuclear power plants, or the needed hydrogen fuel cells. I only did the platinum. I didn't get a metal content for everything else. But it could all be summed together. Right. So it's all summed together. The red is the total metal required, EVs, batteries, wind turbines, solar panels, using a 4-week buffer for wind and solar only. That's red. This is a log scale, by the way. The blue is, instead of 48 hours, let's use 48 hours only. 4 weeks goes to 48 hours. That's not good enough, I can tell you that right now. The yellow is reported global reserves as stated in 2022. The black is what we produced in 2019 in mining. Now, you might notice that the black and the yellow are simply not enough, remembering in 20 years we do it all again. Most cars were ICE in 2020. In 2018, renewable power accounted for 4% of power generation. The vast majority of the system's not been constructed yet, and as such, it cannot be recycled. But if it was all constructed next year, let's say it all just magically happened, that it would not be till 2033 until large enough volumes be available for recycling. Now, I'm also involved in recycling projects as well. The technology in its current form is nowhere near good enough to recycle the volumes needed. But at least the first generation must come from mining. Conclusions. Current thinking has seriously underestimated the size of the task. Battery chemistries other than lithium ion should be looked at, and they will be looked at. We can make batteries out of sodium or fluoride or zinc, but we've got to do it. We've got to develop the value chains to actually do it, instead of, less talky, more wickety whack. That's what's required there. So there's a projected mineral shortage. Production rates and mineral reserves are not, neither one are good enough. They're just not. And there are supply shortages for nickel, cobalt, and lithium now. And those structural supply shortages will remain the same at least till 2025, because no new mines are coming online and they take time to build. So metals of all kinds are about to become much more valuable, and evolution of the industrial ecosystem is highly likely. There's a coming renaissance for the exploration and mining of minerals, I believe. And that's it. Done.
Wow. That is really it's really shocking for those of us who, don't study this. It's very surprising news. And I know that there are some people who have some questions for you from our MEER community who would like to ask.
So I'll stop sharing.
Stop your sharing. Yeah, that would be great.
And the chat. All right. There's nothing...
yeah, actually they'll be coming on. I'll introduce them now and you'll see them. And
okay.
So Chloe Romero is a sophomore at Stanford University, majoring in Earth Systems on the Energy Science and Technology track and minoring in computer science. Her interest in environmental issues started with her time at the NGO Fridays for Future in her hometown of Montevideo, Uruguay. She hopes to pursue a career that works with climate change solutions that are equitable and effective. We also will be having Kyle Kimball is currently a legal master's candidate at Vrije Universiteit Amsterdam, focusing on climate-induced migration and legal redress for the global south. He recently graduated from Tallinn Technical University with a degree in European law, and in his free time enjoys weightlifting and urban exploration. And then finally, Paul Majdowski is a full-time climate activist and political risk analyst from Berlin. Previously, he has completed postgraduate education at Fletcher School, Tufts University, and studied international relations in Dresden and Beijing, and also worked stints in international climate negotiations and the renewables sector in specifics. So welcome to all three of you, and we're looking forward to hearing what you have to ask.
Hi, Simon. It's great to meet you.
Hey, Chloe.
So my first question is related to how efficient each energy source that is necessary for a clean transition is, but more in relationship to their use of minerals. So what would you say is the optimal mix of renewable energy sources or clean energy sources from the perspective of which one uses all of these minerals and metals that you mentioned in the most efficient way, and also in relationship to how efficient their energy output is?
A simple question. I like it. All right. So what I found very simply is when I lined up all the energy systems, I found every single one of them had problems. Every single one of them worked fine on a small scale when it was supported by a larger system somewhere else. But when it became the dominant system, every single one of them had logistical challenges. So I think the entire green transition at the moment is based on the idea that our engineering will stay the same, as will our society. So the first and most easiest thing to change is actually us, not our energy systems. As in, that is, we've got to rearrange our society to a new social contract, and our estimates of what we think the future will be are going to have to be very, very seriously revised, or they'll be revised for us by reality. Right now, the first task that we could do is not to go for the energy systems themselves, is to go for our technology. At the moment, the computer you're looking through is dependent on clean power that's sinusoidal and stable. The power grid that's powering it requires power to be stable 100% of the time, all the time. And the grid is massive. It covers thousands and thousands of kilometers. And that's our technology at the moment. Great. But I think we will be forced practically into a series of microgrids, that is localized grids that will connect. Sometimes they're connected, sometimes they're not. They can drop in and out, which means our technology, our computers, for example, can tolerate very, very rough power. They can tolerate power blackouts. They can tolerate things going up and down. So our technology's got to be geared to accept not only less power, but less quality power. Because at the moment, if we get like a series of power spikes, all our computers would fry. So that's probably, it may sound strange, but I think that's our first job, re-engineering our technology into something that can actually cope with a rough power grid. Then have a very hard look at what we use power for. Like we're very wasteful at the moment. So if we tasked our power to, in a Maslow hierarchy of needs, a micro power grid will run that hospital, or they'll run that smelter, and just that smelter. and all the support systems around it, all the houses around it to run that operation and keep it going. And so it's like society will become event-based and result-based. Whereas at the moment, we have this massive grid that just has power running smoothly just because we need it, with the idea that we have no idea what the power is being used for. The next thing we need to do is get an information gathering system that actually collects information in terms of what we use power for and how do we use it more effectively. And so then we can get to the idea, well, which power system is most useful. Hydro is the best performer by far in terms of when you balance everything up, but it can only be put in certain places. Like anything that is good for a hydro system has one already. We're not going to be able to find 16,000 new hydro sites on the planet. Nuclear has its place, but I think the spent nuclear fuel problem is its Achilles heel. Solar, I think, is a problem. To make solar, a solar panel, the solar wafers, the silicon wafers need to be heated to 2,200 degrees Celsius. At the moment, we use coking coal to do that. If we knock out fossil fuels, a lot of our manufacturing capacity will go with it. If we have to go to non-fossil fuel heating systems, you can get to that heat using biofuels, but that's putting more pressure on the environment and what we extract from it. So I think solar panels will struggle, but wind turbines may not. So it may well be true that wind turbines might be our best and most flexible system, but the idea of actually sort of having a proper buffer behind each wind turbine may be impractical. Beyond that, I actually haven't done the numbers properly on what will be more sensible beyond those limitations. I know that doesn't necessarily help you in the way you hoped, but that's as far as I've gotten.
Yeah, that's more than helpful. I think that's all the time for me, so I'll pass it on to the next person. Thank
Cool
you.
degree, by the way. That degree you're doing, very nice, very nice.
Thank you.
Hey, Simon, pleasure to meet you. Read
G'day,
your
Tom.
work before and was just across the water from you very recently
Right, okay.
over in Tallinn. My primary question, I feel, is in your work, you describe the need for a radically different system of governance to meet this challenge of mineral blindness. And you sort of touched on that with the question of resource prioritization. My question would be how you see this system functioning and what attributes it would need for it to embody for us to even have a chance at a green transition.
Okay, so we've got to change our relationship with energy, possibly also with each other, but also with minerals. It all has to change and shift around that. Now, if we're moving into a world where there's just not enough to go around, we've either got to agree to cooperate at some level, or we turn on each other and it's give war a chance, which actually is the free market action. So what I'm proposing is, see, all human systems in the past have allowed for growth, or they've depended on growth. So what we're now facing is unprecedented, and all past solutions won't work. So whatever we do next, if it is to be successful, something about it is going to be completely new. So what I was suggesting is we take little bits from everything as a start, right? And the idea was, if we extracted resources, and this includes recycling resources and biomass resources, if we were able to extract resources and then we agreed upon, like, each region will have a certain share. And so this is the collective thinking. But then you got the idea of free market, which is the most efficient way of doing anything. So once you've actually agreed on what resources go where, then the system changes, and then you have like a bottom-up approach where what we do with those resources is down to innovation. So from a bottom-up approach, we have our free market capitalist approach. From the top-down approach, we have a more collective, can we sort of share and get along and remember that none of us really have enough. And to hold that all together is the social contract, which agrees that this is the way we should do things. We all have to be consensual that this is what we're going to do and this is why we're going to do it. So then we're going to have to let go of things like consumerism and materialism. That's going to hurt. It's
Excellent.
going to be ugly and it's going to be messy.
Yeah, I think a lot of us are anticipating those growing pains or reverse growing pains. Thank you so much. I think that's my time.
Okay. Well, talk to me.
On that cheerful note, preparing for this call, I had the impression you have one of the most interesting jobs out there, to be honest.
Yeah, I think great.
I think acknowledging the last 50 years after Limits to Growth, this is kind of exactly where we are. Like what the guys 50 years ago predicted kind of is happening around us. And I don't think many people really connect the politics. My background is more in social science. So let me speak from that perspective to what is happening in the geological and material world, basically. Can you go into your 3 paradigms? I think when you were talking with Nate Hagens, you mentioned the 3 paradigms. In my words, I would put them as there are groups of there are basically 3 different groups of people, like good weather friends, bad weather friends, and maybe weather forecasters. You use different words. If you want to go into this.
There's now 4 groups. Someone challenged me over a beer, and yet there are actually 4 groups. Society will split into 4 groups that will interact. The first group is what I call the cornucopians, the ones who claim that there is no problem. You know, leave me alone, give me my stuff, nothing will change. Now, these people, we've all met them, people you cannot talk to. You simply cannot get through to them, and they will defend the status quo way of doing business as usual right to the bitter end. You cannot talk with these people, so wave goodbye. Leave them to it, and if they are successful, learn how they did what they did. Right, the second group is the group I call the Vikings. I don't have enough stuff, but you've got stuff, I'm going to take it from you, thanks. Now, we're seeing a bit of that at the moment at the geopolitical level, but I think we're going to see some very human behavior. Why do the hard work of creating something when you can take it from someone else? Right, that's group 2. I believe that won't last very long, because it'll become apparent where that will perform well in the short term, but in the medium and long term, that's going to become very high maintenance, especially when things like trust start breaking down. Group 3 is, and the Vikings was the one we added. So group 3 is the group of people who go, okay, the world has changed, society has changed. Never mind why it is or where we're going, but now let's look at the practicalities. In a short-term context, like in the next season, where do we get our food from, our heat, our energy? How do we make sure the people around us can live? How do we make sure that society won't tear itself apart? In a long emergency, like one damn thing after another. So that's group 3, and they're actually, you know, the salt of the earth. They're the people who will make sure that society continues. The 4th group I call the Arcadians. Now, the Arcadians will look at how do we make a genuinely sustainable society that is able to maintain the level of technology and knowledge we have now, and things like human rights. We all believe we have human rights and we're all educated, right? That wasn't the case 500 years ago, right? And so if we go backwards, we'll lose a lot of that. So how do we maintain that? How do we maintain a genuine high-tech society that doesn't need fossil fuels, has learned the lessons of climate change, and has developed a more sensible relationship with the planet and each other? So then you have something like the Venus Project, but that might take 60 or 70 years to build. That's not the sort of thing that is done next week. So the Arcadians will have to be working with the, I call the realists, group 3. So group 3 and 4 are joined at the hip. They will have to actually work together. Some people are actually working, you know, they will do work that only their children and grandchildren will see the benefits of. Other people are looking at the here and now needs. And so I see 4 groups. It's just an idea. It's in a way of getting my arms around things, but there's a whole spectrum of solutions in solution space that talk to those 4 groups. The most high maintenance is actually going to be the first group who claim everything's fine. Give me some of your food. It's just a short-term emergency.
Thanks very much. Can I just for half a sentence jump in? For the entire electric power analysis in the beginning, I would mention the potential upside risk of, or positive risk of geothermal technologies advancing. If deep geothermal or other technologies are really pushed by political and industrial power, I think there might be an slightly more optimistic analysis than you've presented so far. But otherwise, thank you so much.
So geothermal, I've got geothermal tripling in size. Helsinki is looking at having all buildings in the future heated with geothermal. So that's a thing. So yes, it's going to be effective. There is a very deep drilling sequence that claims that if they drill deep enough, they can get really, really hot steam out. They can generate electricity. If that is true, then yes, that'll work. But now think about the logistics of drilling so many holes so deep. How long will that take? And how long will it take to construct the power systems to do it? Then put that up against our need for our existing systems to run smoothly. And even like a bad weather year is enough to actually knock our stock market on its knees. Right, so that new technology, let's say that works, and it may. Let's say it does. It will not arrive in time to save our glorious stock market. So all our systems are quite fragile. So now we've got an economic problem, and our industrial capability will go with it. Thus, we will see the disruption and the reordering and the social contract. Now my work on that note was written to be made obsolete. It was written for the express purpose of calling out what I call the bullshit that I was seeing coming out of Brussels and the European Commission. They were making some spectacular predictions that were clearly not practical. And so I actually took all what they thought they were going to do, and that was actually the scenarios that I developed. These guys have their hands on future scenario planning, and they're delusional. So my plan was to shock them out of that delusion and at least have a conversation. Like you said, well, let's do geothermal instead, or something else, or have some sensible ideas out there. None of that exists at the moment.
Oh, God.
I think we want to give a chance for our live audience also to ask some questions.
Mm-hmm.
So if you have, so I want to thank you, Kyle, Paul, and Chloe for your questions. And so if people from the audience have questions, you could go ahead and send them in the chat to Bud. And initially, there are a couple of questions that came in specifically about ocean mining. So, what your opinion about ocean floor mining is, and the opportunity for more minerals, and also ecological and justice risks. And there's a paper that's quoted about the legal aspect of ocean mining. And someone else asked about the seabed authority's power to, does it make sense? Is there a need to resist that? What action should people take around that? So yeah, if you have anything about that.
So danger, Will Robinson. So yes, there are deposits on the seafloor, and some of them are quite rich. But mining, operating under seawater at depth is really, really tricky. Like, it's really tricky. It's not easy to, in fact, it's easy to operate in outer space. Salt water is very corrosive, then you've got currents and everything. And so the logistics of actually mining off the seafloor, again, it can be done, but it'll only come up in very small quantities. We're not going to deliver 24 million tons of copper to the market a year, right? But let's say someone works out how to do that, where they can get so much metal off the seafloor. Now, to do that, they're talking about, for example, like something like an open pit, or even an underground operation. That will stir up so much sediment, and all clouds of sediment, and it will literally kill off what's left of the sea life in a large region around each mine. And for it to be useful, we're talking about thousands of mines. So let's say someone does actually work out how to do this. The question, should they do it, is, well, how are they going to limit the ecological impact of ocean life, considering most of the ocean life at the plankton level is already deteriorating and crashing, and ocean acidification is a genuine problem. How do you think mining under the sea is going to go to deal with those things? I would suggest that we don't do it for that reason alone.
Yeah, that makes a lot of sense. We have a question from, let's see, we have a question from Brent. Do you think concentrator PV or thermal PV would be more scalable than regular PV from a materials and energy standpoint? Have you done any analysis of mirror manufacturing at scale?
Not at scale, not directly. I do know, I did look at an analysis of a CSP plant that actually failed, and that they were not able to, by the time they could actually get their operation to go, they could not deliver on their targets. They had real problems in scaling up and delivering power. There were a whole lot of maintenance issues involved, and the cost of operation was exorbitant, much more than they thought. I think it's a great idea. The concept is a great idea, but I think it's only half developed, as in more needs to be done. Can it be scaled? I don't know. I actually don't, I don't know. I would suggest the wrong question. Like, instead of scaling it up, scale our needs down. And so if our needs shrink, and we, instead of having like a massive grid that's got to be balanced, you have a power grid off a CSP plant that's actually tasked to one single industrial park that supports, say, like 10 industries. That will work. Right, so scale down what we need to match what we have.
Yeah, great. Here's a question from Mark about whether these forecasts are really theoretical or are they physically, possible?
So that's a nasty question, right? So what they are practical. It's a straight engineering calculation. How many cars in the world? How far did they go? If they were EVs, how much power would come off the grid? Mm-hmm. The end. So the size is practical. The believability, as in, is this a sensible idea? It very quickly shows that they're actually not realistic. And the whole purpose of the work is to show the current plan is a crap plan and it will never happen. Mm. Right? And someone's got to come up with a better one. I presented at the United Nations last week and I said those exact words. And then I showed up a chart showing that peak oil could be in our past. Currently, peak oil is November 2018. We won't know if that really is the date until we get to, say, end of 2023. Stop clowning around. We need to be operational now. And the existing plan has logistic bottlenecks that are just simply not viable. So to answer your question, it's theoretical, as in, I don't believe it will ever happen and it's not practical.
Mm-hmm. Right. And also it's based on today's population, or is it also based on the increasing population on planet Earth?
It was based on 2018 population.
Right. Okay. Right.
Right. And so the UN predicts the power grid will be 4 times the size in 2050.
Right.
Ho, ho, ho.
Yeah. This is a wake-up call. Here's a question from Bud, actually, about ammonia. It is important to update analysis to ammonia as highly dense and safe hydrogen carrier for use in internal combustion engines of all sorts.
Yep.
this is a game changer, but that is as yet unknown in public circles. Do you have any comment about
So,
that?
when I did my work a couple of years ago, a lot of these things didn't exist, or if they did exist, they weren't defendable. And I needed something that was actually defendable. Like a lot of people say that's not practical unless I could get it off the market. Like when the first generation of work that I did crashed because I was relying on a lot of these what ifs, right? And so I had to go, what was actually commercially available at the time? Yes, we'll come up with new ideas, but each of those new ideas will come up. For example, that will require a lot of ammonia. How do you make that ammonia if you're not going to use the gas industry? So in other words, the technology of using ammonia, yes, great, good idea. But what are the resources required to make it viable and then scale it up to usable for, say, a task across the planet? And so what would be the energy requirements and feedstock requirements to make that much ammonia? And how would you do it? Would you use, what I've put forward is a very crude calculation, and there's certainly more things we can do. For example, you could have a thorium reactor. I love thorium, by the way. Thorium reactor's pure job is to make hydrogen with the heat. Never mind the electricity, the heat that comes out of a thorium reactor can be used to directly manufacture hydrogen. And we've got these big ass ships. We don't need to put batteries in them. We can go back to sail. We've just got to scale down our expectations. But our current expectations and strategic plans will do nothing of the sort. Anyway, so back to the ammonia. I have read a few papers on it. Yeah, it looks interesting. I haven't included any simulations in it. I did one simulation to illustrate the point, and the people who need to get it have gotten it. Now they don't know what to do. Right, and so the next work is now more solution-based.
Yeah. Okay, we have a question from Dr. Tao, actually, from Yale. And so this has a couple of different parts to it, but the prohibitive material requirements you convincingly demonstrated seem to apply for conventional batteries featuring relatively rarer elements like cobalt, lithium, and nickel. Do you have plans to consider material feasibility of alternative energy storage systems such as, one, the molten metal battery using metallic electrodes of magnesium and antimony with an electrolyte consisting of chlorides of magnesium, sodium, and potassium. Two, chemical cycle storage such as calcium oxide and calcium hydroxide, hydrogen dehydration cycles. And third, molten silicon thermal energy storage. So
yes, and yes. Right, so at the moment, this will surprise you that even after I presented this information now for a year, in Europe, they will not look at seriously anything other than lithium-ion chemistry. They believe the future is lithium-ion chemistry in some form. Like all these new things like LFP batteries, they still require similar quantities of, lithium, nickel, cobalt, manganese. They're all the same elements. Now, for the future, says we can make batteries out of all sorts of things. Like there's a guy here in Osanimi who's making batteries out of table salt. It's like a version of the sodium battery, but an evolution beyond that.
Right.
I personally like the idea of the zinc air battery or the fluoride battery. Fluoride as in what's in your toothpaste. So my solution for the future, because we've left it so late, and there is a rare lesson in manners coming for our industrial systems. There's a round of tough love coming, and it would be funny if I wasn't living through it. So my future solutions is to develop something so simple that the average person could make it in their workshop. So what if we were to get something like fluoride minerals and make batteries out of that we can actually put together? And this guy I know has a lab where he's taking industrial minerals off the shelf and he's making batteries. They're not very good batteries, but the batteries he doesn't need someone from China to make them for him. He's doing it. Right? So
Yeah.
we scale back our expectations of performance. Like a lot of those solutions that you rattled off sounded, I haven't looked at all of them, no, but they also sound very complicated. Like, what is the complexity behind each one in terms of where do we get the materials from and where are they manufactured? Because most stuff is not manufactured here. It's manufactured on the other side of the planet. And so we will be required to develop stuff locally. So we will most certainly have to become simpler. And it is possible. Right, so that list that you just said, that's, remember I was talking about the 4 different paradigms. That's a list the Arcadians would be interested in.
Right. Well, I think I know probably what the answer to this is. Philip asks, how do you expect future mineral and ore extraction rates will be affected by both declining quality of ores and the rising costs of energy to extract them?
Badly.
Yeah.
So, hi, Philip. So what, we've got a series of reserves at the moment, but they're based around the idea that mining actually is used with fossil fuels. Like all the energy, like a power station is generally run by gas, which is attached to a mine, and that powers all the equipment. And then we've got the truck and shovel fleet, which is run by diesel. So if we're going to increasingly poor resources, we need more energy. In fact, there's a 450% increase in the energy consumption in the mining industry between 1973 and 2008. So in that short period of time, it's gone up so much, and it will steadily go up. So if we go into a non-fossil fuel world, all of a sudden the technology that we've got at the moment, at least, is not very good in terms of performance. Like they've got mining trucks, right, that are electric, and they sound good, but the metrics of performance, like a diesel fuel truck can run for 24 hours without refueling. An electric vehicle truck lasts about an hour before it has to go and recharge. Right, so it's like a PR. This is the start of the technology. Will it get better? Sure. Will it get better fast enough? To know about that. So if we move into non-fossil fuel mining, a lot of our existing resources reserves will be downgraded to resources and they're just not viable. And then we get to the point where all our rubbish dumps that are around us all of a sudden are much more valuable. So what we call recycling and mining may well merge into one discipline, but it won't deliver nearly enough metal to give us what we need, right? And so that's what I'm saying is scale back our expectations on all fronts, in all directions, and all things.
Yeah. Yeah. So then, so Jamie asks, what about the byproduct of algae blooms as a resource for energy?
Okay, I did look at that. Biofuels was, the simple question was, if we could take all the petroleum products, jet fuel, gasoline, diesel, and bunker fuel for marine, and we turn it into biofuel. And I looked at using ethanol to make gasoline and jet fuel, and soybeans to make biodiesel and bunker fuel. And the third thing I looked at was algae. And I was really surprised. This came as quite a shock to me, actually, when I did it. But the energy required to produce a portion of fuel off algae was 10 times more than what actually came out of the algae. It had a very negative energy return on energy invested ratio. So someone's going to get that going. So a lot of research and development and breakthroughs are required to make that viable. Much more energy is put in compared to what you get out. And then you've got the problem of we don't have the actual space in coastlines to make enough algal ponds to produce enough fuel in enough volume to be of use.
Yeah. Okay, well, I don't think we're going to be able to get to everybody's question today, but I have 1 or 2 other questions. Tom asked if you could direct us to some articles that present this kind of information or in a similar form. So there's anything, you could also just send those to me afterwards, and I can send them in the follow-up mailing, or if it's easy to post something in the chat.
I just posted in a chat.
Mhm.
Oh, Rachel Donald, hello. I know Rachel. So I just put in a YouTube of a YouTube presentation I gave to the University of Queensland, and that actually goes through a discussion of these numbers. As to other sources, other people, I actually don't know. I actually don't know who else is doing this precise work. A few people are alluding to the same thing, like they've started to do the math associated with the amount of minerals that we need. But as far as I know, no one's done work quite like this. The question from Rachel was, LFP does not require nickel or cobalt. So let me find out what actually is in those exactly. Because I actually had each chemistry to come together. Where's working files? Metals, final reports, quantity. So I'm actually in the process of finding out the metal content for each one. Just bear with me for a second. So each one, so LFP, lithium iron phosphate. And so that's lithium, and I think an iron. But that's only a part of the actual market. Like in the market, you've got ratios of you've got lithium, you've got all the NCA plus, you've got the NMC series, you've got LFP, and you've got solid state. And LFP batteries are representing only a portion, and they're basically lithium and iron phosphates. But the other chemistries certainly do require nickel and cobalt. Yeah.
Mm-hmm.
And so I've actually went through and actually calculated that based on those chemistries. Hi, Rachel, how you doing? Rachel does some good work, by the way. She does a podcast called Planet Critical. Check that out.
Definitely. Okay, we have a question from Louise about what about the amount of finite water needed to mine that will become non-potable after mixing it with acids? You had mentioned about the ocean acidification and the process of seabed mining and all of that. But her question is even, a little bit in a different direction.
Damn good point. So as we're grinding finer and finer, we are using more and more potable water, and it's harder to recycle. Potable water is becoming a resource that's becoming a problem. I did not include that in my numbers. I just included just the actual metal at the end, but I got a whole report on the limits of linking the mining of, here we are, mining of minerals linked to the limits to growth. So I'll put that in the chat. So what you've alluded to there is a real problem. And if we increase mining a lot, then we're going to hit that as a very real problem. Hey, you got something from Rachel. Hang on, what's this? Here's an idea for you. Category something else. Has data on electrifying transport that you'll find interesting. Okay, business presentation. I will look at that. Download. So yeah, and so my work's pretty crude. It's a really, really simple calculation. It's not rocket science, and it's to make a point. And there's a million solutions out there, but we're not doing them.
Right.
We're going after the things that won't work.
Well, we have one closing question. You're saying that the whole system needs to change. And how soon do you feel this needs to change? And what do you see as possible?
We should have started 20 years ago, which means that would have been a more sensible, comfortable thing. I think it's not so much is when do we get a shock that we think, oh, maybe we shouldn't do that then. I think for Europe in particular, this winter will be a dress rehearsal, and all sorts of things that were considered taboo at the moment might be talked about in the supermarket in a couple of months' time. Now, the process is something like this. First, we've got to understand the true nature of the problem and all its moving parts. At the moment, we will focus on one thing only. I often talk to environmentalists who will talk about carbon pollution, but then I'll ask them some basic stats about species die-off, and they have no idea what I'm talking about. Right, and that to me is a far more serious problem. So we need all the moving parts understood. The second thing we need to understand is what are the limitations of any given system or solution we might put on the ground for the future. And then third, for the first time ever, we can start to make a credible plan. Steps 1 and 2 don't exist at the moment. There's just guys like me, shouting from the rooftops, we've got a problem, do something, do something.
Yeah. Well, I think this is probably inspiring people to take action on this subject, to, tell other people what you've learned today. So we want to thank you so much for coming and presenting today, Simon. Really appreciate everything you've shared.
Okay.
Here at MEER, we are working to help educate the public, and also while we are working on a solution to the warming of the planet. So we invite you to visit our website, and we are an almost 100% volunteer staff with just a few paid student researchers at the moment. So we encourage you to make a donation if you haven't, or even if you have, to consider making another one, or making a monthly donation, which is also possible at meer.org/donate. And these donations help to fund the materials and sensors for solar reflector field experiments, as well as basic expenses for the researchers. So we thank you for coming today. Next MEERTALK will be on Sunday, November 6th. So please keep that on your radar screen. And it's really wonderful to see you all. Thanks for coming.